everybody, today we're talking about mathematical induction. Induction is used when we want to prove a statement is true for every positive integer, not just for one example. You'll often see induction used for formulas, patterns, divisibility properties, inequalities, and statements involving counting or sequences. The basic foundation of induction is that it proves the statement is true for every integer by building a logical chain. A lot of times people will use a domino analogy to show how it works. The idea is step 1 shows the first domino falls. That's our base case. Step 2 says if we can show that one domino falls, the next must fall too. That's our inductive step. Then step 3, our conclusion, shows all dominoes fall, so the statement holds for all integers. The common structure of an induction proof looks like this. We first start by stating our proposition or conjecture. Next, we prove the base case. Then we assume our proposition or conjecture is true for all pk. After we have our assumption, then we'll prove that our proposition is true for all k plus 1. Once we do that, we can conclude the statement holds for all integers in the domain. Let's look at a couple of examples. We'll start by looking at the sum of the first n integers. Our conjecture is 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 over 2. We often call these sums triangle numbers. Triangle numbers are numbers formed by adding the first few positive integers together. They're called triangle numbers because you can arrange the dots in the shape of a triangle. So let's get started with our base case. This means we're substituting n is equal to 1. So on the left side, we just have the number 1. On the right side, we use our formula, 1 times 1 plus 1 over 2. Because 1 times 1 plus 1 over 2 simplifies to 1, we can see the left and the right are equal, and the statement is true for the first integer. So now we'll move on to our inductive step. This means we're just going to assume the formula is true for n is equal to k. That means 1 plus 2 plus all the way up to k will be equal to k times k plus 1 over 2. Now we want to move on to show the formula works when n is equal to k plus 1. So our first step will be to add k plus 1 to both sides. So we add it to the left and we add it to the right. On the right side, we can start by making k plus 1 into a fraction with a denominator of 2. That means we have 2 times k plus 1 over 2. Because we have a common denominator, we want to put these two terms together. Before we do that, let's distribute the k to the k plus 1. That gives us k squared plus k. We can also distribute the 2 to the k plus 1 to get 2k plus 2. Adding the numerators together gives us k squared plus 3k plus 2. Notice we're leaving the left side alone and we're only working on the right side. Now that we have a quadratic, let's try to factor it. Factors of 2 that add up to 3 would be 2 and 1. So now we have k plus 1 times k plus 2 over 2. We're going to rewrite the k plus 2 as k plus 1 plus 1. That way it looks like our formula of n times n plus 1 over 2. I have k plus 1, then I have k plus 1 plus 1 over 2. Since we have shown the statement works for k plus 1, we have proven it is true for all n. Let's try that in another example. This time we're looking at the sum of the first n odd integers, and we're given this conjecture, 1 plus 3 plus 5 up to 2n minus 1 is equal to n squared. So here we're looking at a pattern. Notice we're starting with 1, and then we're adding 3. When we add that 3, notice we have a square. Now we're going to add 5, and when we add that 5, again, we get a square. So what we're trying to show in this formula is that every time we add another odd integer, we're going to form another square. So let's get started by looking at our base case. Our base case starts with n equals 1. So on the left we have 1, and on the right we have 1 squared. So we move on to our induction step, which says we're going to assume this is true for n is equal to k. That means 1 plus 3 plus 5 all the way up to 2k minus 1 would be equal to k squared. We need to prove this for k plus 1. So we have to think about what does k plus 1 look like in this situation. It says where it said n, I want to put in k plus 1. So I'm going to add 2 times k plus 1 minus 1 on the left, and I'm going to add 2 times k plus 1 minus 1 on the right. What did I do? I added one more odd integer. On the left side, we're going to leave it alone, but we want to work on the right side. On the right side, I'll distribute the 2 to the k plus 1. Now I have k squared plus 2k plus 2 minus 1. We can put the 2 and the negative 1 together to give us k squared plus 2k plus 1. Now we're going to look at this quadratic and see if we can factor it. Factors of 1 that add up to 2 are 1 and 1. That means k squared plus 2k plus 1 can factor into k plus 1 squared, which shows us the formula is true when n is equal to k plus 1. Since the formula is true for k plus 1, that means it's true for all n. In our last example, we'll look at divisibility. We're going to prove that 7 to the n minus 1 is divisible by 6 for all positive integers n. As always, we'll start with our base case if n is equal to 1. 7 to the 1 minus 1 is equal to 6, and we know 6 divides 6. So we're going to assume that the statement is true when n is equal to k, which means 7 to the k minus 1 is divisible by 6. We want to prove this is also true when n is equal to k plus 1. The first thing we want to do is say since 7 to the k minus 1 is divisible by 6, that means 7 to the k minus 1 is equal to 6 times x for some integer x. Then we can multiply 7 to the k minus 1 and 6 times x by 7. 7 times 7 to the k is 7 to the k plus 1. 7 times 7 is just 7. On the right side, I want to leave the 7 times 6 alone. The key step is what I do next. Instead of writing minus 7 on the left, I'm going to write 7 as 1 plus 6. Since the 1 and 6 are in parentheses, I know the negative applies to both of them. So I have 7 to the k plus 1 minus 1 minus 6. I'm going to take that 6 and move it over to the right-hand side of my equation. Now I have 7 to the k plus 1 minus 1 is equal to 7 times 6x plus 6. Notice that both terms on the right have a 6 in common, so let's factor it out. That looks like 6 times 7x plus 1. This shows me that 6 divides 7 to the k plus 1 minus 1, which therefore proves our original statement. So in closing, induction is one of the most important proof techniques in mathematics. It's especially useful for formulas, sequences, recursive definitions, and divisibility. The key is to prove one case, then prove the chain continues forever.